The lecture today, I will start by reviewing the problems on chapter 1. And the problem on chapter 1, we have three types of them. First is called analysis. And the analysis separated into analysis 1.A and 1.B. And another one we call design. That is different. When we talking about the analysis, what we have is going to determine the stress. We have the equation sigma equal P over A, and we have tau equal V over A. By this kind of problem, Ajahn will provide you the information of the cross-sectional area of the structural member. It's going to be very simple structural member, and it's going to be very simple structural connection. Okay, there is two of them, and most of the time this one is for structural member, and this one is for structural connection. And then what you need to do, there is going to be a structure, okay? And by doing that, you got to use the free body diagram and the equation of equilibrium to determine the internal forces in structural member and internal shear force in the structural connection. So this is going to be the problem to determine the stress. The second one, the problem will rewrite this equation to determine the force. Okay, that means we are going to have P equal to sigma times A. And also the shear force will be equal to tau times A. And again, by this kind of analysis problem, we are going to provide you the area. Okay, and then what we have is the stress is going to be the allowable stress in order to determine the internal forces in structural member and internal forces in the structural connection. What is going to be tau allowable? Tau allowable is going to be the strength of the material divided by factor of safety. Okay, if we test the material in the lab, you will get the strength such as you may know from the engineering material. You have the class of engineering material. For when you take the first year or maybe the first trimester of the second year, you may know we have a lot of engineering materials such as steel, such as aluminum. Okay, and those kind of things has this. We call this is the yielding stress. That's come from the test of the material. Okay, and the test must follow some specific standards such as Thai industrial standard. That is going to be what so-called MOOC in Thailand, or in short, you may call this one as the TIS. Okay, and by following this is a shear yielding stress. This will be provided to you for the first chapter, but in the third chapter, you are going to determine it. Okay, and to analyze this kind of problem, we're going to provide you with the factor of safety also to make the structure safe under some unexpected phenomena such as high wind force and such as earthquake. That's going to be a lot in Indonesia and maybe some in Philippines. So you got to have factor of safety. We have typhoon also in Thailand. That's kind of unexpected force. So by doing this, you're going to know this also. And then when you compute for the P and for the V, you can use the free body diagram and equation of equilibrium again, changing the internal normal forces, internal shear forces to be what they're asking for, such as the applied loading. So this is the problem to compute for the applied load. And the last one in design, we write the equation again in the design. From this equation, you are going to determine the A, okay, the size of the cross section. So you take the A over here, so the equation is going to be P over sigma allowable. Again, we are going to provide you with the allowable stresses. By rearrange this equation again, you going to determine the area. But this one, you're going to use the V divided by the tau allow, and we will give you this. And the same work as before, you're going to use the free body diagram and equation of equilibrium to determine the P and V. By doing this, you will get the size of the structural member, and you also get the maybe the diameter of the pin of the structural connection. That's the whole thing for chapter 1. If the problem is the written examination, you're going to work on one of this problem. But anyhow, you got to know everything. And if the examination is the multiple choice, you got to know everything also. So no matter what it is the objective of learning. What is so-called the learning objective? That's you guys supposed to know about the problem about analysis and the problem about design. Okay, that means you got to know. Not only know, you should be able to solve it. That means you should have skill to compute for everything that I just lecture you guys. Okay, that's all. Do anybody have problem with this introduction? Anyone? Pisa, do you have any question to ask me? No one have problem? Okay, if no one have any question, let me go a little bit further. We come to the conclusion that the problem have 3 types. One is analysis to determine the stress. Okay, the stress for some specific point is maybe normal stress, is maybe shear stress. When you know about the cross-sectional area, okay, you may know the dimension of the structure and connection. That means you know this one, you know this one, and you know about the applied forces in which you use the free body diagram and the equation to determine the internal normal force and the inertia. And the second one, this is going to be a little bit tricky to determine the large jet load that can apply to the structure. From the previous example, if you may recall from the example analysis 1.b, we have the load of 71 kilonewton for the failure of the lot, if you remember, or 168 for the failure of the aluminum column, and 183, if I remember, that is the failure of the connection. And then you determine the large loss. But the answer that you're going to provide to Ajahn is going to be 168. Remember? By this kind of problem, you determine this 168, but it's going to mean the larger load. That's kind of applied to structure because the load P that act on that problem will increase from 0, 100, 150, 160, 168, and the aluminum block fail. When aluminum block fail, the whole structure considered fail. Okay, and by this problem, you just write P equal to sigma A, and you write V equal to tau time A, and this is going to be allowable. Okay, you may have this kind of problem again following this PowerPoint. And analysis, that means you determine the dimension of the structural member basis on this equation. You determine the dimension of the connection basis on this equation. So this is the conclusion of the problem that we have. So let us start by determining the stress for this structure. This same structure can be used, this picture can be used to design these three kind of problems. First one, let us consider this point A. A is going to be the connection basis up on this picture. Guys, this connection is what? Is a single shear or is going to be double shear? Anyone answer me, please? The connection at A?
It's a double shear.
Okay, it's going to be double shear. Good. And this one, if you know the connection at A is double shear, this is going to be what? This picture
Single shear.
is single shear. So the pin A is going to be double shear, and pin B is going to be single shear. And the diameter of the sub B, the pin is over here, is going to be 16 millimeter, and the diameter of the pin A is going to be D sub A equal to 12 millimeter. Okay, usually the double shear is going to reduce the shear force that's applied to the pin. So most of the time, the double shear connection has a smaller diameter compared to the single shear. Okay, then we come to the lot. We have the lot BC. The lot BC has the pin at B and the pin at C. And there is no detail about the connection at C. Okay, so you can neglect it. That means they didn't care about this. But by considering this lot, okay, is pin at B and pin at C. This is a kind of two force member. And as you may see, this one has the diameter of 14 millimeter. So this is going to have the circular dimension with 14 millimeter diameter. So what they are going to, what the problem asking you, you are going to determine the shear stress as the pin A and pin B. That means you are going to determine the tau sub A and the tau sub B, and determine the normal stress in the lots BC, sigma sub BC. Before you can determine this, you got to find F sub BC and then divided by the area. So this one you know from the given diameter and the forces over here. We will use the free body diagram and the equation of equilibrium to determine it. So let's go. We going to draw the free body diagram of this beam AB. Ajahn, how about the beam AB? The beam AB will be discussed later in chapter 6. So just consider the simple connection and simple structural member such as the two force member. So the cable the rod BC is the two force member. So over here, we are going to have the T sub BC. And over here, we have the pin, okay? And this pin is going to have the A sub X and A sub Y. And this is going to be a type force. So if you know the free body diagram, let's start first, okay? You separate the structure. That means you draw this beam, okay? This one is going to be the beam. And then you may also set the X, Y coordinate, okay? Usually the X, Y coordinate can be just simple as this is X in order to set A sub X, and this is Y in order you guys to know about the Y direction. So maybe the second set the X, Y coordinate. And then the third, okay, you put the known forces. Okay, this one you just put the 15 kilonewton. And force is going to be, you put the unknown forces. This is going to be T sub B, A sub X, A sub Y. And the fifth, you just put the dimension such as the length, okay, and the angle. So you put this one, 3, 4, 5, 1.2, 0.6. Just do the review of this. And again, you have 3 unknown. You have the total of 3 unknown. You have 3 equations. So most of the time, we not use the summation of the force in this computation, because if they don't provide the direct answer, usually we take the moment. When take the moment at A, for example, we neglect the A sub X and A sub Y. So by doing this, we can determine the T sub BC directly. And later, we use these 2 equations to determine the A sub X and A sub Y. Okay, let's take the moment at A and take the counterclockwise as the positive. Why? Why you take the counterclockwise? Because the T sub BC, when you separate the component over here, the T sub BC in this component will time what? This is the vertical, will time 3 divided 5. This is will provide the counterclockwise direction, and it is the unknown. That's why we take this as the main thing. Now, the component of this force provide what? Provide 0 moment, because the line of action cut to the point A, and you got this one T sub BC time this one time 4 divided by 5. We will use this one later. So by doing this, you got T sub BC time 3 over 5, and then you have this one as the moment arm. This is going to be 1.8 meter, and this is positive. And 15 kilonewton is going to provide the rotation clockwise. So that is going to be negative, reverse to this. And it's going to be 15 times this length is 1.2. So you just carefully put the number into the calculator. We're going to use the same calculator, but no. Okay, use the same one as the edging static and carefully do so. So a lot of students, they can do it, but they just mistype the number into the calculator and get the wrong answer. If you get the wrong answer here, everything later will be wrong. Okay, so very careful about this, Yoeng. And then you get what? You get the answer. That is 16.667. Now things going to be get a little bit easier. Summation of x sub x. You use this equation, and then you said the a sub x, okay, is going to be in this direction. This is going to be positive. A sub x is positive. T sub BC times 4 over 5 in the opposite direction is negative. This is going to be very easy answer. And then summation of f sub y equal to 0. Now, a sub y is here. You put upward as the positive. So a sub y is positive. And then t sub bc times 3 over 5 also be positive because it's upward. And 15 is downward. So you get a sub y equal to 5 kilonewton. These two forces are the component of the resultant at point A. In actuality, over here, the force over here is there is the R sub A as the resultant force for the A sub x and A sub y. And this one is the real force that's act on the pin at A. That's we are going to determine it more. By doing this, you just square root of A sub x square plus A sub y square. Just put them together. Okay, you get the resultant force. And again, this R sub A, okay, will act to the pin at A with the double shear, and at point B here, there is this force acts on the pin at B as the single shear, okay? And again, this force will act on the lot, on the lot BC to produce the sigma sub BC also. Okay, so we will have tau sub B, we will have tau sub A based on double shear, tau sub B based on single shear, sigma sub the stress in the lot BC by the sigma sub BC is going to be normal stress. So for the pin A, double shear, that means 14.14 must be divided by 2 because by the double shear, the shear is going to be R sub A divided by 2. By doing this, we got 7.12 kilonewton. And then tau equal to V of A is going to be easily. And by putting the number into the equation, there are two units, okay? Some going to use the meter square, but we know that the Newton per millimeter square is also going to be megapascal. Most of the time, I also use this. So by doing this, my tau sub A will be 7120 Newton divided by and then radius square is going to times 6 square. That is going to be in Newton per millimeter square. Or you may use this one if you prefer. You are going to get the same result, but depend on which one you prefer. Now, the B is single shear. Okay, so 16.667 is going to be the shear over here. Okay, and then you just divide it by the area. You got the stress. And most of the time, Ajahn may provide you with the sigma allowable, tau allowable. If you have the tau allowable of what? Of 63.0 megapascal. So the stress occur at A is less than tau allowable. So this pin is going to be okay, or it's going to be safe. But for this one, the stress occur at B is larger than tau allowable, which is 63 megapascal. This is going to be no okay, or it's going to be unsafe. What is going to be recommendation? What is your recommendation for this? What is going to be your recommendation for this? You going to what? What your recommendation? Anybody? It's not safe. What is going to be your recommendation? No one provide answer. กง ธนพล ชลิดา นัทพงศ์ Oh, somebody type it. What is increase the diameter? That's great. That's good. You are going to be a good engineer. Okay. Thank you, Charles. By doing this, you're going to recommend it to make the section larger. By making the section larger, okay, by enlarge, what's so called enlarge D sub B. How do you know what is going to be D sub B? You're going to what's so called redesign. Okay, if you like to redesign it, you're going to rotate it. The A required, okay, is going to be the V sub B divided by this one, sigma allowable, tau allowable. So the problem is going to be 16,667 divided by, this is going to be Newton, divided by 63 Newton per square meter. So what is going to be? You just cut this one, and you will get this one in the millimeter square. So this is 667. Okay, put in your calculator, divided by 60. This is going to be 264.56 square millimeter, and this is going to be pi r sub b square. So you can find r sub b divided by 3.1416, and then you do the square of this. It's going to be 84.21. It's going to be 84.21. Let's put it into the calculator. How come my calculator won't rotate? Okay. Then square root 2. Okay, it's going to be 9.18 millimeter. This one y.18 millimeter, and then you're going to determine the diameter. So you times it by 2. That is going to be D sub B. That's required to make this connection safer. It's going to be 18.35 millimeter. The problem is when you go to the Home Pro, when you go to the construction store, we didn't have 18.35 millimeter. You may go over there, may have 18 millimeter or 20 millimeter. Which one you are going to use? Which one? Okay, somebody answer me. You're going to use the 20 millimeter. You select the larger one to make this connection safer. Okay, I do some expansion of this problem in order you guys to be understand about how you check the connection is safe, how you check this connection is unsafe, and how to correct it by redesign it. When you redesign it, you will get a larger diameter. When you get the larger diameter, when you going to buy it, you're going to buy the bigger one. Okay, and I should note that if Ajahn didn't say about go to the store, buy the correct diameter, you got to answer it by what you get from your calculator. Okay, everybody, you're supposed to be okay with me, right? Not yet. We go to the next one. Okay, we're going to check the lot. Okay, the lot is going to be in tension, and the tension going to produce the stress that is going to be T sub BC divided by the log BC. Just determine it, going to be very easy. Again, it's up to you. Somebody may just put this one, the force, divided by pi and then r square. And this is going to be in a millimeter square. You're going to get this one in Newton per square millimeter, or this one going to be megapascal, or if you prefer the second method, you just put everything into the calculator, you will get the same thing. Again, this one will compare to the sigma allowable. Usually, the sigma allowable is going to be yielding stress of the steel divided by factor of safety is maybe the 250 megapascal divided by factor of safety of 2. Okay, this is usually 2. So this is going to be 125 megapascal. And since the stress sigma sub BC is less than sigma allowable, so this is going to be okay, or it's going to be safe. But by somehow, you guys like to use a larger factor of safety. It depends. อาจารย์ will provide you for this kind of problem. Okay, if you expand this one to be 2.5, the allowable will be 250 divided by 2.5. This one again specified by engineer. Okay, it depends on how you like to set it. By doing this one, this is going to be 100 megapascal. So this is again no K. This is going to be unsafe. You're going to be redecided. When you redecide it, it's going to be larger than this. Okay, how do we going to redecide, Ajahn? It's going to be very easy, guys. We just come again by this equation. We're going to determine this one. Okay, and then A sub BC, sometimes we said it's going to be required. Okay, in short, it's going to be REQ. Okay, D is the same. It's going to be this one up, and that is going to be F sub BC, and then divided by this sigma allowable. So what we have now is going to be equal to 16,667 Newton divided by 100 Newton per square meter. So this one, you will get the answer of 166.67 millimeter square. Again, this is going to be pi r square. And then you can determine it 166.67 divided by 3.1416. So 53.05. And then you take the square root. So it's going to be 7.28. So the R is going to be 7.28 millimeter. And you times it by 2. So the D, okay, is going to be 14.57, say 14.6 millimeter. See, it's a little bit larger. When you go to the store, they sell it for 15 millimeter or 14 millimeter. You guys got to select the bigger one. Only this. So the problem 1.A can be crossed to the design by using this kind of concept. Okay, by doing this kind of concept. So any question for my first problem from your guy, Kubet?สวัสดีภูเบศครับ
Nothing ครับ
Okay, I don't know did you get me or not, but this kind of problem, you may have it in the examination. It's not directly 1 point A to B. It can be related analysis 1 point A with the design. Okay. Liam. Kim Sophia Liam.
Yes, I can.
You get what I'm teaching you, right?
Yes, I can.
You don't have any question?
Not yet.
Not yet. Okay. Good. So let me move. Baldonado. Angelo. Baldonado. How are you?
Ajahn.
Yes,
good,
Ajahn. How are you?
I'm good, Ajahn.
Yeah, okay. You good. Oh, you good and go further. Kim Hoi Young. Are you here?
Ajahn. Yes, Ajahn.
Okay.
I got it. Yeah.
You get right what I'm trying to show you here
Yes, Ajahn.
by modifying the example.
Yeah.
Okay, let me go a little bit further. Now, the problem changed. From the previous problem, we know the force P that's applied over here to be 15 kilonewton. But for the problem 1 point B, the problem changed. They are asking you to determine what's going to be the P. Okay, what's the largest P that can be applied to this structure? Okay, by provide you with the dimension of the structure and the allowable stresses are given. So by doing it again, we come to the pin A, which is double shear as before, and then we come to the pin B, which is going to be the same thing. Okay, the same as before, nothing changed, single shear. And this is going to be 16 millimeter as before. And over here, we have D sub A as before to be 12 millimeter. And then they provide us with the allowable shear. Okay, so by this problem, they ask us to determine the Pmax in which this structure can resist by comparing only the connection. Okay, so we have what? Tau equal to V over A. Tau sub A equal to V sub A and A sub A. Since this one is double shear, so tau sub A is going to be R sub A divided by 2 times A sub A. Okay, and we come to this one for the pin B. We have tau sub B equal to V sub B divided by A sub B. Now, this is single shear. This is single shear. We are going to have tau sub B equal to, the V sub B is going to be T sub BC divided by A sub B. So by doing this, you can determine T sub BC equal to tau allowable. Change this one to be the tau allowable and time A sub B. So you get this force that's applied to this connection. And again, by the force, by the stress as pin A, you determine what? You determine the R sub A is going to be, change this one to be the tau allowable. That is going to be tau allowable and time 2 of A sub A. And then you will get R sub A. The R sub A will be related to the force P by what? You use the free body diagram and equation of equilibrium to determine the P. Okay, over here, again, you also going to use the free body diagram and the equation of equilibrium to determine the P. So you're going to have P based on the force at B. Okay, and you will get the P basis on this connection at A, okay, and then you got to compare them and select the answer, okay. This one a little bit easier than previous one, only two condition of force P are going to be compared, okay. The previous lecture we have 3 to compare, okay. I just make it a little bit simple for and easy to understand. So we check this one, change to P, and if you have the previous result, okay, you just divide it by 15, okay, you just divide it by 15, and then you times it by P, okay, use the P times it divided by 15. The same thing occur here, okay. The force over here, the force R sub A is going to be this one divided by 15, and then you're going to times it by P. So based on the concept over here, we can find the new reaction by divide the reaction from the previous example by 15 and multiply it by P, okay. Why? Because it's proportion to each other, okay, just proportion to each other. So you can just do this computation, and then what we have, the R sub A. By doing this, you got to have R sub A equal to 0.9493, 15.24 divided by 14.24 divided by 15. You get this one, and the other one over here, 16.667 divided by 15. You get this one. You get this T sub BC. Oh, sorry, I didn't get this one. Okay, you get this force. Now, what's next? Go to the equation that we have. Go to the equation that we have. Go to this equation. Okay. Okay. Let's go to the equation. The pin at A. The pin at A subjected to the R sub A as we know as before over here equal to this one. Okay. And what the from the equation over here, what the force is going to occur. So the R sub A is going to be equal to the tau allowable 100 megapascal times 2 of A sub A. Since this one is the double shear, okay, double shear. So the force V sub A is going to be R sub A divided by 2. So you just put R sub A divided by 2 into this equation, and then you will get this one for 0.4746p. Half of R sub A is going to be the shear. And then let me put it again. Tau sub A equal to A sub A divided by A sub A. What we are going to find is V sub A is going to be tau sub A sub A. It's going to be tau allowable A sub A. Okay, by doing this, you just put this one, the tau allowable. Oops. Just rearrange it. This is, they didn't write like this. Okay, it's okay. It's okay. This is going to be tau allowable. This is going to be tau allowable 100 megapascal equal to this is V sub A. Okay, this is going to be 0.4746p, and then divided by A sub A. By doing this, we are looking for P. Okay, just put everything to this one, and then you get the P. The P. Rearrange the equation. You get the P of 23.83 kilonewton. And for the next one, we have tau allowable equal to V sub B divided by A sub B. The V sub B, since is single shear, is going to be this one. Okay, and the A sub B determined from this. You just put everything together by the same way. 100. This is tau allowed. V sub B divide A. So you can solve the next one for the P. For this one, you got the P to be 18.1. Okay, if the P is 18.1, this one gonna fail. This one gonna fail. This pin at B gonna fail. So again, from the previous discussion, the load increased from 0 to 10, 11, 12, 15, 16, 18, and then to the 18.1, the structure failed. Okay, this problem is easy because this problem didn't discuss about the lot BC. Okay, if you prefer to taking care of this one, Ajahn will provide you what is going to be sigma allowable. Okay, let me specify sigma allowable equal to tau allowable of 100 megapascal. Can you determine the force due to the failure of the lot BC? I think you can do it for sure because the sigma allowed is going to be T sub BC divided by A sub BC. So Ajahn going to provide you the A sub BC also. By doing this, you will have this one 110 power 6 equal to this one 1.111 P. And then what the size of this? Let's put it the size of 16 millimeter. Okay, so this is going to be pi and then time 0.008 square. Now you can determine the P equal to something kilonewton. Okay, by doing this, let me put it into my calculator. That is going to be 110.6. Okay, pi. So that is going to be 20.11 kilonewton. 20.11 kilonewton. Okay, by doing this, the answer still be this one by setting the D sub BC equal to 16 millimeter. Again, Ajahn modify this problem a little bit. Ajahn check D sub BC to 12 millimeter. So this equation change 110 power 6 equal to 1.111 P divided by pi, and this one is 12 millimeter. So this one gonna be 006 square. Now, what is going to be your answer? Okay, what is going to be the P for this one? Just modify thing. Okay. Okay. And then it's going to time. We get it 11.31 kilonewton. Now the problem, the answer to room check. Since you reduce the size of this lot, okay, the force P that will cause the failure of the lot reduced to 11.31. So now the answer is not that one. The answer change. The answer will be this one. Okay, you guys, can you catch me by expanding this example a little bit? What did I do? Why I said the answer is 11.31?
It should be the lowest force, Ajahn.
Okay, the lowest
prevent the
from
failure.
what you get. and the answer is going to be the P Mech, right?
Yes, Ajahn.
Okay, everybody. Lisa, are you here? Lisa Hin? Lisa Hin,
Yes, Ajahn, I'm here.
you here, and you understand why the answer is 11.31, right? Why Ajahn didn't say the answer is 23.83? Why? Because Ajahn looking for the largest load P, but the answer in the opposite direction. Lisa, can you give me the answer of that? Anyway, Lisa, you go back and think about
Yes,
it.
Ajahn.
Why is 11.31? If you don't understand it, just ask Bandonado. Okay? Okay, I did modify this problem in order you guys can see how Ajahn going to design the example. We can design any examination and example basis on manipulating the number. And don't just go to the tutor and trying to guess what the problem gonna ask you, because it can change, it can move everywhere. If you do a lot of practice, you're going to get the skill. You're going to develop the skill, and you can solve any kind of problem. Okay, the last one. Let me go to the last one before we break for 5 minutes. So let's see. If I don't modify it, the answer is going to be 18.10. Okay, again, they may ask us if actually we know the P max is 18.10 and the P right now acting on the structure of 10 kilonewton. What is going to be the factor of safety of this structure? You just divide the P max by the current P. Okay, and then you get that 1.81 as the safety factor. That means you can increase the P a little bit more. Okay, you can increase the P a little bit more. Okay, next, let us do the design. Okay, the design, they ask us to determine the pin A and ask us to determine the pin B and ask us to determine the diameter of the lot BC. Again, we come to the area equal to the stress, the force, divided by the allowable stress to determine the lot BC. Since the lot BC is in tension. For the pin A, okay, you're going to find the A of the pin A. That is going to be the shear at A divided by tau allowable. So what you have is the tau allowable is 85 megapascal. Okay, they provide you directly, and also for this one, the sigma allowed is 110 megapascal. You can use this sigma allowed to determine the area of block BC, the same as the B. Okay, and by doing this, you got to use the free body diagram and the equation of equilibrium to determine the internal shear force and internal normal force. Let us just do the same thing. It's going to provide us the same answer for the free body diagram and the equation of equilibrium. The R sub A is going to be 14.1. Okay, the force T sub BC is going to be 16.667 kilonewton. Because of what? Because it's going to be the same free body diagram and the same equation of equilibrium. Okay, A is double shear, B is single shear. Just move this one. BC is the two force member, and then the problem will be the same. I will go by this slide. I won't say about this. We did the computation to determine the T sub BC, the T sub BC, and we also did compute for the R sub A, okay? And then we're going to decide it. The pin A is double shear, okay? When the pin A is double shear, the R sub A 14.24 divided by 2, we're going to get V sub A, half of it. And then the diameter is going to be easily determined, okay? And then I'm going to ask you again, it's depending on the way you like to compute it. You may use the Newton, and then over here, 85 megapascal, 85 Newton times millimeter square, and you put it like this, you're going to get the answer in millimeter square, and that is going to be 7120 divided by 85. That is going to be 83.76 square millimeter, okay? And if you prefer in meter square, you know that that's 1000 millimeter equal to 1 meter. If you square it, 1 square meter is going to be 10 power 6 millimeter square, okay? You can convert it easily. And then you're going to determine the diameter. It's going to be pi d square over 4. And then you get 10.4 millimeter. And in the market, you have 10.0 millimeter. You have 12 millimeter. You select the bigger one. Okay, many people understand this. We get the bigger one to make the connection safer. Let's say safer. And then we go to the pin B. At the pin B is in single shear, okay, due to the T sub BC. So this time we're going to have V sub B equal to T sub BC. Now we just put it over here. Just put it over here, and you may get the answer to be 196.1 square millimeter, or 196.1 10 minus 6 meter square. And then you do the computation again. You get D sub B of 15.8 millimeter. You use the bigger one to make it a little bit safer. Okay, simple, right? Design, that is simple. And then you got the lot BC. The last one, the lot BC. You do the same thing, but just change the stress into the sigma allowable. It's not allowable because the lot is going to be in tension. So you get the same thing, the answer. That is going to be direct. Okay. And then when finish the design, you will get the diameter of the lot A. Use 12 millimeter at the pin B. Pin B, 16 millimeter. For the lot BC, 14 millimeter. And note. If Ajahn didn't ask you, do not ask you about the diameter, okay, that you buy from the store. If Ajahn didn't ask you to do this, you just use what you get from the calculator. Okay, beware about this. If don't ask, don't select a bigger one. Just use the one for the calculator, because somebody didn't care about the problem statement. They just neglect it and do it what I teach you, and sometimes you get the full score because of this some small mistake. Okay, so you must use what you get from your calculator. Okay, to make it clear, I mark it over here. So next time, if you make this kind of mistake, you won't complain about, I didn't tell me about this. Okay, and that's it for the chapter 1. We may have, I provide you some more problem for diligent student to solve for this, and there are some more example. I would like you guys to go and study, since we don't have much time to teach you about this. I will come back later before the examination to provide you with this kind of writing. But for the meantime, you must study by yourself. And there are three homeworks. You got to turn in 7 days from today. That means you're supposed to turn in this one before Christmas, December 23rd, okay, 2021. By that, Pioria waiting for you on this. Pioria, today you are here. Say hi to your student if you are here. Pioria. Okay, end of chapter 1. Let me take 5-minute break. Okay, on the next chapter, chapter 2, we're going to talking about the strength. Before we talking about the strength, I suppose again mention about what we study over here. We have materials that we use in our engineering, and usually we call it engineering material. The main material is maybe steel, is maybe aluminum, is maybe copper, is maybe brass. Okay, that's a lot of metal material, ferrous and non-ferrous material. But sometimes it may be hard to see the deformation of this kind of material under the force. Okay, when it's subjected to forces, it's going to have some deformation. So sometimes in this study, we use the rubber, okay, as the example. You may use the very simple rubber band. Okay, when you pull the rubber band, you can see its deformation. When the structure is in tension, it's going to have the elongation under this kind of axial force. And if it's subjected to compression, it's very simple to see the contraction of the structure. Okay, so you may say, before you put the force into this structure, okay, the length between my finger is 2 centimeters. Again, if I poke it, you can see it's measuring to 3 centimeters. So by doing this, before Ajahn apply the force, the length here is 20 millimeters. After Ajahn apply the force, the length change to 30 millimeters. So the deformation, we use the delta. This we call the delta. It can be L sub F, L sub final minus L sub O, L original. So this is going to be very simple to compute. Okay, 30 minus 20, that is going to be 10 millimeter elongation. But in engineering, we didn't much directly related to the deformation. We use the epsilon. This is going to be epsilon. Is called for the normal strength. And again, I suppose to say under the force produce the stress equal to the internal force divided by A. This normal stress produce the normal strain in the same way. Okay, tension produce elongation, and we just define the normal strain equal to the deformation divided by its original length, or may you write it into L sub F divided L sub O minus L sub O divided by L sub O. Okay, and then in chapter 3, we will talking about this kind of tension test. Okay, tension test in the lab. The tension test must for the steel, okay, must follow the Thai industrial standard, okay. Or if you go to your country, stand DARD, you must also follow your country standard, okay. And then by doing this, we will put this sample, into the machine. We call the testing machine as the UTM, or universal testing machine. When you put it into this universal testing machine, when the force is 0, okay, the L sub O is 2, then you increase, okay, during the increase of the force, the deformation just get larger and larger. There is a computer program that will generate the graph that relate the epsilon with the sigma, or relate the normal stress by the normal strength, and that's going to occur in chapter 3. Okay, so usually the chapter 2 will be combined with the chapter 3, okay, to produce the examination if it's written examination. But if it's multiple choice, we can ask anything. Okay, by doing this, you can see when the force is 0, the point is 0. When we increase the stress, the strain increase. And usually for the rubber, that I show you, most of the time the stress strain relationship of the rubber is linear. Okay, but as you study in the engineering material, if this is going to be the steel, okay, the steel will have structural steel yielding over here, and that's why we define the yielding over here as the sigma sub y, and use it as the strength of material. And as you may know, again, when you test the structural steel until the failure, the curve will look like this, and that's why you study the deformation in the form of epsilon. Okay, we will use this to determine the mechanical property of the materials. Okay, properties of materials. Okay, that is going to be in chapter 3. But anyway, we got to have the knowledge of chapter 2 first. So first, understand the concept of deformation. This is the concept of the deformation, okay, of the deformable body and structure. And then you got to be able to determine the normal strength. This is normal strength. And also the shear strength. The shear strength is a little bit different from this one. Okay, you may use this support, and then when you apply the force into this sponge. You see, this one, the first one is in the normal angle. When you apply the force, the sides of this sponge just move. Okay, let me put it this way. This way, we have a sponge. Okay, this sponge fix it in my hand over here, and then we apply the shear force. The shear force is different from this one. This is normal force. This is going to be shear force. And when you apply this shear force, this one will change the shape like this. And then we define the angle over here as the shear strength. Anyone have some problem?
มันดมมือตัวเองดู
Hello? Any problem? Pin Pacharapon, you didn't turn off the microphone. Please. Okay. So the noise won't disturb us. Okay. We define this change in angle as the shear strength. And by doing this, the gamma, the shear strength, is start by the normal angle that you see over here. And then you just minus this pi over 2 by this angle, theta palm. Okay, so you get this angle. And this one will have the unit in radian. But this one will have the unit, the normal strength, millimeter by millimeter. That's the concept of shear strength. Okay, and then you may use this one again and go back to try to see the change in this one due to the shear force. And then you be able to determine it. Okay, I said it's going to be very easy because we will use it later in chapter 3. There is 2 problems. Okay, in this analysis, the rigid beam is supported by the pin at A. This is a pin. This is a pin. Okay, and cable BD and cable EC. The force P, okay, cos NC move to 10 millimeter. That is going to be downward because the force P is downward. So this is 10 millimeter. The same thing. Okay, you may imagine this one. Okay, usually the start is going to be here, and then when you put it, this one going to be like this. The beam is very strong. So the center line that's passing through the centroid of the section will change into this one, and then you can see the cable BC will has this elongation. This is going to be the elongation BD. Okay, you may say this is delta BD equal to this one, and also for this one, you may see it's going to move 10 millimeter. This is delta EC. Okay, that is going to be the elongation. So they ask us to determine the normal strength. Okay, so this is going to be normal strength of EC is going to be delta sub EC divided by L sub EC. Very simple, right? Very simple if you understand the problem. Okay, and for this one, the normal strength BD is going to be delta BD divided by L sub BD. Very easy. And the second one, the plate, let's see, steel plate, the electron steel plate, A, B, C, D. That's when it starts. This steel plate is rectangular, okay, is have the normal angle over here. And then on the normal angle over here, due to the force, okay, I believe the force, they didn't show the force, but I believe the force will move in this direction. So the rigid line over here will move to the dashed line, and then they asked us to determine average shear strain occur on the plate. Okay, you know shear strain is the angle over here. Over here, you can find it easily if you use your definition that I just discussed. Okay, you got to have to determine the angle theta star over here in order to put into this equation, and you get the strain occur here. They're very simple, and we use this one later in chapter 3. Okay, come back. Deformable body usually maybe structure. The body can be the structure and can be the machine. Okay, is will subjected to external forces and external temperature. The deformable body will tend to change its shape and size. The same thing over here. Okay, under the force P, BC, EC, BD, EC get elongation. Elongation is the deformation. And also for this plate, subjected to, we don't know the size of this force, but we know the deformation. Okay, so there is two things. When its intention is going to get the elongation, okay, and then the length here is going to be the elongation by putting the measurement of this one to be L sub F, measurement for this one to L sub O, and by this linear displacement, we define normal strain equal to L sub F minus L sub O divided by L sub O and call it epsilon. And another way, we have you may use your finger, okay, and then you twist it. Most of the time, Ajahn did a simple thing: mark a line along the finger, just mark the line like this, and then when you twist it, you can see the line twist. The same thing occur if you mark the rectangular over here, and you do the twisting by this way. You're going to twist this way. Okay, you're going to twist this way, and this element will change the shape into the white shape. Okay, and then again do the definition. This is pi over 2, and this is the angle. You get this one, and I said this is going to be in the radian unit, and the previous one is going to be millimeter by millimeter. We call shear strain gamma. Okay, linear displacement also occur due to the bending. If you bending, okay, this one is going to be bent, but the aluminum ruler is hard to see. If you use the rubber, you can see. If you apply this kind of moment, you get on the top for the elongation, the bottom for the contraction. By the deformation of the bending, there is the middle part, usually is passing to the centroid of section, has the neutral, okay, no elongation. Got to understand this. And when you test the structural material or engineering material in the tension, usually we put this one, and then what we have, the stress equal to P over A, and also is will produce the elongation. Okay, the strain equal to elongation divided by L sub O, and then you may put the point on the strain strain diagram, and then you get this thing. And most of the time we are interested in this first portion. If the yielding is not clear, okay, if the yielding point is not clear, such as for the aluminum alloy, unlike the steel will has the very clear yielding point like this. This is for the steel. That's I mentioned before. The sigma sub y is easily to determine, but for the aluminum, you got to use the 0.2% offset to determine it. And then we have the relationship for the linear portion, sigma equal to E epsilon. And we call this as the modulus of elasticity. Okay, now for the application of the material in the engineering structure, most of the time, the relationship between stress-strain is going to be what's so-called linear and elastic. What's so-called elastic, like a rubber. I pull this one, okay, 2 centimeter to be this one. When I release the force, it's come back to 2 centimeter. That's called linear and elastic. And the displacement usually is like a vector. It has the size, the magnitude, and has the direction. Theoretically, okay, linear displacement is moved from A to A part. Okay, and the angular displacement is mean change in the angle between the given lines, like this. So this one produce the normal strain. This one will produce the shear strain. And then for the normal strain is defined by the elongation or the contraction divided by its original length. So by doing this, you measure the final length, and then you minus it by original length, and then you divide it by original length. So you get this one in the normal strain. And the unit usually is millimeter by millimeter, because the deformation usually is very small. And then if you write this equation properly, so by putting this delta sub S and strain average equal to delta S palm minus delta S. So this delta S palm, okay, can be approximate by what? By delta S palm equal to, take this one, delta S strain average plus delta S, and rearrange it. It's going to be 1 plus strain times delta S. So by doing this, you can determine the final length by knowing the original length and knowing for the strain. That means you can determine strain by this equation, and you determine the length by using this equation. Okay, and mathematically, the strain defined by this equation, we don't use this one much. We're going to use this one a lot. Okay, and then for the shear strain is the change in angle. Okay, shear strain is gamma, and the change from what? From the pi over 2 or 90 degree. But they didn't use 90 degree because the unit of the shear strain is in radian. That's why they use pi over 2 and then minus by zeta palm. Okay, and if zeta palm is less than pi over 2, that is provided positive. That means it's going to be something in this one. Okay, but if it's like this, it's going to be in negative. Okay, and in the Cartesian strain component, we also have the cubic element, and we can determine the strain in 3 axes, X, Y, and Z. Okay, and usually we didn't much consider the problem in this subject in 3 dimensions. Most of the time we just consider it in only 1 or 2 dimensions. So this one is a concept. Okay, we will use it properly later. We also use this one in the master degree course called Advanced Mechanics of Material. For the strain, usually is very small. For example, did you see the deformation that I pull this ruler? No, it's going to be very small. Okay, again, the rubber is large. Yes, the rubber is large, but most of the engineering material, aluminum, copper, steel, brass, they also has very small strain. So when the number is small, such as 0.002 is small. So why is 0.002? If you come back to the strain that we discussed before of this one, you can see actually in this length of linear elastic, the strain that we are measured is only small, 0.002, or even though as the yielding that is also about 0.006. So when you compute for the small, very small number, such as you time it together, it's going to be very small. Okay, so we have some at first order approximate analysis for this kind of thing. Okay, for this also it said the normal stress that we measure at this point is about 180 megapascal. That's produce the strain only 0.002. So normally the normal strain is very small, but the normal stress is 180 10 power 6. Normal stress always large, normal strain always small. Okay, and then first order approximate analysis is going to be like this. If you have 1 plus deformation or strain power n, you can approximate it to be 1 plus n small deformation or small strain, such as 1 plus 0.001 square. 1 plus 0.001. If 0.001 is here and n is square, you get this number. And then you put into this one, you can see they are very close to each other. So it's going to be simple to use this one. And then if you time this, you can put this one also. For the angle, when the angle in the radian unit is very small, sine of the angle is going to be the angle. Cosine of the angle going to be 1. Okay, cosine of the angle going to be 1. You can put this one and compare. And the tan is going to be tan of the angle is going to be the angle. This one can check by putting everything into your calculator. Now, the problem usually is not in the examination, but for the multiple choice, it's maybe. So just consider it. Okay. So this one is very rigid. Okay. This one is very rigid. No deformation under the application of the force. Only the wire over here, the wire BC, the wire, this one will deform under this one. So when you move, this is going to be the rotating point because it's the pin. So when you pull this one, the wire BC will change to the B palm C. Now, what is going to be the average normal strain occur in this situation? Okay, that is going to be strain of the BC is going to be B palm C, the final range, minus the original range of the BC, and then divided by the BC. So the problem is going to be geometrical analysis to determine the length. BC is okay. BC, we know this one, BC is going to be 2L, and this one also 2L. So what is going to be B palm C? Okay, by doing this, we got to understand the line, the pink line here. When you move it, it's going to be this one. Okay, to be this one. What happened is the length over here is L. When you rotate it, the dash pink line is going to be L. And if this is theta, so the length measured in the vertical going to be L cosine theta. Okay, and over here going to be L sine theta. Now you got this one as the L sine theta. You got this one as the L cosine theta. And then if you project this one and set this is the normal angle, you may find the B palm C or C B palm. It's going to be the same thing. B palm C or C palm B palm. It's going to be what? It's going to be the length here square plus the length here square. Okay, so the first one is going to be 2L plus L sine theta, and then you get this length square. And for this one, this is L, this is L cosine theta. So this one is L minus L cosine theta square. So you just expand it to be this equation. Okay, just take this one and then you have this one to be 1. It's a property, sine square theta plus cosine square theta. Okay, if you won't follow, just stop it and do some computation. And then what we have, this one is going to be a more simple equation, but it's still hard to compute it. So you got to do the approximation. Approximation of what? Approximation of the angle theta, because this small, this very supposed to be very small. So the sine theta going to be theta. The cosine theta, that is going to be 1. So 6 minus 2, that is going to be L. This is going to be square root of 4 plus 4 sine theta. Okay, and then this is maybe 2L square root of 1 plus sine theta. So you can reduce this one. And this one is going to be 2L times 1 plus sine theta is theta already, right? And then it's going to be 1/2. So that is going to be 2L, 1 plus theta power 1/2. And then that is going to be approximately what? This one approximately 2L times 1 plus 1/2 theta. And then this is going to be a little bit simple. You got CB palm. So put CB palm into this equation, minus by 2L divided by 2L. So approximately the average stand on the wire BC going to be 0.001. That is very small as we do the approximation. And then sometimes we didn't do only the tension test. We did the torsion test. By the torsion test, we put this sample into this machine and we rotate this handle. That's going to produce the torsion applied to this specimen. And then the torsion T will be equal to, the tau, the torsion T will produce the tau, and the tau will be, this has the diameter, so the radius is equal to the diameter over 2. You use the vernier, okay, so you know the R, and then it's going to divide by J, and the J is going to be pi R power 4 divided by 2. You can go back to ending static and take a look at this polar moment of inertia. We call it polar moment of inertia. Okay, this is also known. So everybody known. So the shear stress can be measured and compute. And again, over here is the digital meter. Okay, it's going to provide you with the strength. So you can plot the shear stress and shear strength. And this is going to be studied in next chapter. This property is used to design the shaft. Okay, design the shaft. The shaft is what? Is in the car, transfer the force, the torsional force from the engine to the wheel of the vehicle. Okay, so this also important test. Again, the shear strength is going to determine from the equation such as pi over 2 minus zeta star, and the normal state is the deformation defined by the original length. Now we consider the steel plate. Under any kind of force, the steel plate has deformation. So the deformation is the dash line. Now they ask us to determine the normal strength along AB and AB palm. The AB is original. AB is original. Okay, and then AB palm. The AB palm. AB palm. B palm supposed to be this one. So average normal state is depend on this. So the AB now is going to be 250. Okay, and what is going to be A and B palm? We got to determine this length. And the length of this can determine from what? The deformation over here. So we do the computation of this. Okay, over here is 3 millimeter. So it's caused the deformation here of 3 millimeter, and it also has this vertical of 2 millimeter. Now you can see this is going to be 3 millimeter, and this is going to be 248. This is 248, and this is 3. So you can determine AB palm by using this equation, 248 squared plus T squared. That is going to be AB palm. So this is going to be what? Negative normal shear stress. So this is going to define the contraction of line AB into line AB palm. Negative means contraction. Now we go a little further. The same problem. We find the average shear strength with respect to the XY axis. So what we have is going to be, this is shear strength in the XY direction. So that means we are looking for the angle here. So this is going to be pi over 2. What is going to be zeta palm? So pi over 2 is no. It's going to minus zeta palm. What is going to be zeta palm? Now we come over here. This is going to be 3 millimeter, and this is going to be 248. So we can determine this angle directly to be 3 divided by 248. And again, you got to change your calculator into the radian to get the answer correctly. Okay, and the internal angle can be determined, okay, by minus pi over 2 by 0.41. So the angle over here, you can determine it to be 1.558 radian. Okay, that is going to be very easy, right? Can you change from the radian to the degree? You say by the circular, this is 2 pi radian. 2 pi radian is 360 degrees. So 1.558 radian, that is going to be 360 degrees times 1.558 and divided by 2 pi. So you get this answer in the degree. Okay, you got to convert it later. Now, to the harder problem, we come to this problem. We have the A, B, C, D. Okay, is the in the light black color. And then they ask us to determine the average shear strength under the apply of any force. The A, B, C, D change. The A is still the same, but B change to B part, C change to C part, and D change to D part. They ask us to determine the shear strength in the XY. By this one, that is going to be this angle and this angle. Why? Because by the definition, this is going to be pi over 2 minus theta part, and this is going to be pi over 2, and this is going to be theta part. When you follow this equation, you can get gamma sub xy is the combination of this angle by this angle. Okay, then find the normal state of the side AD. So the first AD is here and it's changed to AD palm. Okay, this is going to be easily. AD is going to be L sub F minus L sub O divided by L sub O. And then they ask us to determine the strain. That's along the line dB that originally is going to be this length. Okay, and then L sub O, and then this one gonna be L sub F. Okay, so strain dB is going to be B palm D palm. Then this one gonna be L sub F minus BD divided by BD. Okay, so for the AD is going to be AD palm minus AD divided by AD. This is the concept of this problem. It's not that hard. Okay, so the first one, the angle will be the combination of these two angles. This angle come from this one gonna be 3. This one gonna be 3 millimeter. This one is 400. Okay, this is the first angle. This one 2 millimeter. This one gonna be 300 millimeter. So you combine the angle together, you get this average shear strength in the XY plane. And then for the AD, this one AD palm minus AD divided by AD, just I mentioned. The AD is going to be this 400 millimeter. This is the AD. So what is going to be AD palm? AD palm will be determined from this 3 millimeter and this 400 millimeter. So it's going to be square root 3 square plus 400 square. So this one going to be in positive. So AD is going to be elongation, Okay, and the harder is this one. Okay, for this one, I just mentioned the dB is easy. The dB can be determined from this one 300 millimeter and 400 millimeter. So this is going to be 500 millimeter. dB is going to be really easy. Okay, and the dash yellow line is going to be harder. You got to go back to the engineering static. Okay, and then you use the law of cosine. Okay, you go back and use the law of cosine. You know this sides. Okay, from 3 square plus 400 square root, and you know this side. This is going to be 2 square plus 300 square. Okay, that is going to be AD square, just I mentioned, and then this is AB square, just I mentioned. And how about the alpha? Go to the problem number 1. Now we have gamma sub xy equal to p over 2 minus alpha. We know this, so we can find alpha easily. And then you put everything together into this equation, and then you get the answer of dB palm. And then the state dB palm minus dB, you get the negative. So this is going to be the contraction. Okay, and that is the end of chapter 2.